session. And we are very happy that Marcus Simonovic from STEM agreed to give lectures on structure formation to tell us how to do precision cosmology with imprecise space.
Thank you. Thanks a lot. Thanks a lot. So thank you for the invitation. I'm really happy to be here. I was just telling earlier to some people that very often to me happens that when people meet me for the first time, they for some reason they think I'm Argentinian. So this is basically like almost like coming home. So okay, I think that you already had one set of lectures about large-scale structure. I wanted to maybe tell you a little bit more about something that I call here the precision frontier. Rogerio told you a lot about some other aspects, and this should be kind of complementary. And so for these lectures, I think that the idea is to talk mainly about these analytical methods like perturbation theory. And I want to tell you a bit about that, what is the context, how people used to think about these things, and maybe you know some of these works like related to the standard perturbation theory, and how this old thinking had several problems that were now well understood and resolved in the last 10 years or so in the framework of the so-called effective field theory of large-scale structure. I'm going to, on Thursday, tell you a little bit about some more technical details related to the so-called infrared summation, bias tracer, and RSD. And this should give us enough material then to basically have something that is good enough to be compared to the data. I will explain what are all the ingredients in this perturbative modeling that we need to compare to the realistic data from galaxy surveys. And finally, on Friday, I will tell you a little bit how do we apply this to BOSS and a few words about some future prospects for this field. So this is our plan, and here I have a few, let's say, lecture notes or little reviews of this subject. And if you really go and Google these titles and these people, you will immediately find these lecture notes. They're very easy to find. There will be some things that I will just skip. There will be some derivations that I will skip in the interest of time. But you can always go there and find more details if you want. Okay, so let us begin, and I want to start showing this this nice image from the so-called 2DF galaxy redshift survey. So in this type of like pictures, each individual point here, I'm sorry, each individual point is, it doesn't work, is a galaxy. And for example, here you see one single slice, narrow slice on the celestial sphere, where you have a map of these galaxies. And roughly speaking, in this map here, there are like, let's say, 100,000 galaxies. And you can see that these galaxies, of course, are not distributed uniformly or randomly. They form certain cosmic web and some structure. And if you want to make any use of this data, we have to find a way to make theoretical predictions for for how this cosmic web looks like given some initial conditions and some cosmological model. And so we have been very good in collecting this data throughout history. If you look at this, the number of the size of these spectroscopic samples as a function of time, you can see that from the beginning of the 80s until today, basically the size of these spectroscopic samples was increasing, roughly speaking, by 1 order of magnitude every decade. Okay, so this of course the first surveys around this time were very important to basically establish the cold dark matter paradigm. And later on, they kept increasing in volume. I showed you the image from this 2DF survey. And the best possible survey that we have at the moment are the so-called BOSS data, which have roughly a few million galaxies in the sample. And there are upcoming data from DESI and Euclid telescopes, which are going to be in the order of a few tens of millions spectroscopic samples. Yeah. And people are even proposing the upgrades of currently existing instruments and future surveys, which will keep this trend of almost exponential growth in the number of objects you observe, and therefore the volume of the universe that you observe. Okay. So now, why are we doing all that? So why not just using the CMB? For example, you heard from Julien about the CMB. You know that this the observation of the CMB was used to really establish the standard cosmological model and precisely measure cosmological parameters. So why we just do not continue to do that? Because clearly it works very well. Well, there are two reasons that I can think of. One is that the information. Let's try this. Let's see how it goes. So information in the CMB is limited. And it is limited by the number of modes that, or number of pixels that goes like L max squared. Probably Cora will tell you more about this. But essentially, we have already, for example, if you think about the temperature maps, Planck already saturates the whole information that you can get. So measuring temperature maps in more detail is not going to bring us more information. And similarly, we're soon going to reach the limit of what polarization data can give us. And so therefore, if you want to do more things or do better things, we have to move forward and look elsewhere. And these galaxy surveys are one alternative. And the second problem with looking only at the CMB is like degeneracies. So here I'm showing two famous examples. So the CMB is great if you really want to measure the cosmological parameters within the lambda CDM cosmological model. However, as soon as you open up the parameter space, if you want to test some either alternative or some extension, things can get very, very complicated. We're not talking about some crazy extensions. For example, Mehrdad has mentioned curvature this morning. Imagine that you allow curvature parameter in your cosmological model and you try to fit it from the CMB. It is very well known that in that case, you cannot constrain omega matter and omega lambda, and you get this very strong degeneracy where this dashed line corresponds to the specially flat universe. And so the way that this degeneracy is broken, actually, is by adding some BAO data. And once you do this, you intersect this like the degeneracy direction, and you find a very nice measurement that Planck usually reports. So galaxy clustering is already important even today to measure, to constrain this extension of the minimal lambda CDM model. Another example is, for example, the measurement of the sum of neutrino masses. If you look at the CMB only constraints, which are given here in this solid black line, you can see that the upper bound at 2 sigma, for example, allowed for the neutrino mass is even 0.3 electron volts. While if you add, again, the information from the galaxy clustering, in particular the measurement of the BAO scale, then you get these blue dashed lines, and you see that basically the error bars are factor of 2 better. And again, this is due to some degeneracy between the Hubble parameter and the sum of neutrino masses, which is very nicely broken by the CMB data. So, so this is just to say that already today, like this information that we have, even in the BOSS data, is very important in order to combine it with the CMB data and get the best possible constraints. And in the future, galaxy surveys have potential to surpass the amount of information in the CMB. And with this increased precision, we need also very precise theoretical tools in order to get this information out. Now, the science case for these surveys is very broad. I will not go into the details, and you probably heard already some of these things last week, and you will hear more this week. But there are, roughly speaking, two different types of things that we are after. One is well, we can use these large-scale structure surveys to ask questions about the properties of the initial conditions. And so many things related to inflation, and I think that Mehrdad will review some of these things in his lectures during this week. We can answer these questions basically looking at the galaxy distribution, because galaxies remember what is happening in the initial conditions. And the second thing is that since the universe goes through a long period where gravity plays the dominant role in this structural formation, since everything gravitates, you may hope to use gravity basically as a tool to discover some properties of like things that you don't have direct access to, particularly in the dark sector. And among many examples, the most famous one probably is measuring the sum of neutrino masses from cosmological surveys, which cannot be done easily in the laboratory. And simply because you have a huge volume of space to integrate over, even a small effect that neutrinos have on structural formation accumulates, and you can eventually clearly see it in the data. And this is one of the most important targets for the upcoming galaxy surveys and for this decade. But we can also ask many other questions. For example, whether the dark matter is perfectly uniform and homogeneous in a single thing, or maybe it has some small subcomponents which are rather different. In some sense, neutrinos are already an example, because neutrinos behave like dark matter, but they're not cold dark matter. So we already know that we have cold dark matter, and we have something which is like warm dark matter, which is actually neutrinos. In that case, we know what it is. But from the cosmology point of view, it really behaves like a warm dark matter. And then the question is like, do we have some other massive but light particles in the dark sector? This is one option. We may have a fraction of dark matter to be an ultralight axion with a very small mass. We still want to put better constraints on spatial curvature, study the accelerated expansion of the universe. We may want to study whether there are additional energy components either in the early or the late universe, and so on and so forth. So there are really many questions that we can ask, and these observations of large-scale structure and galaxy clustering, in particular, I'm going to talk about, is really a nice tool to give some answers to all of these questions. Okay, so now before I move on to some more detailed story, which is a bit more technical, let me finish this motivation part by trying to explain a little bit what does this precision really means in the introduction that Mehrdad gave, and also I wrote in my slides that I will talk a bit about something that looks like a precision frontier. So let me first say that we can imagine that we have some range of scales, and Rogeri already explained to you that basically things can be very different on different scales. So very roughly, I'm going to split things into two parts. Like when we have high K or small scales, things can be very complicated, okay? While we believe that on large scales, things are simpler, and the universe looks much simpler. And it is simple, and I will explain throughout these lectures in what sense exactly it is simple. It is not trivial, but it is simple enough that we can have some, let's say, reasonable control over what is happening. And then you can basically have two kinds of strategies, and there is, in fact, two types of things that you want to do. So one is that to be very precise in the situation where things are relatively simple, or trying to have roughly correct answer in the situation where things are complicated, hoping that you're looking for some effects which are so large that you basically have to see them even if you don't have like very precise theoretical predictions. So to illustrate what I'm talking about, let me maybe try to give you an example in which you can imagine that dark matter has some fraction of some exotic dark matter. So by exotic here, I mean something which doesn't behave like a cold dark matter. Imagine that, like, for example, neutrinos would be one example, okay? But let us imagine the dark matter is even more interesting, and it has like a fraction of dark matter which is warm dark matter, or a fraction of dark matter which is ultralight axion. Think about such scenarios, which are possible, and people would like to put constraints on such scenarios. And so this model is in principle characterized by two parameters. So one of them is the fraction of this, let's call it exotic dark matter. And the other parameter is some scale k star, where there will be some feature related to this model. So for example, if you have some warm dark matter, there will be some free streaming scale, the same way as for neutrinos, which appears in the power spectrum, and this will be this k star. For the case of ultralight axions, for example, you may think that this is related to the de Broglie wavelength of the ultralight axion. So if that is the case, you can ask yourself, how, like, given these two parameters, like k star and the fraction of this exotic dark matter, like what is the how well can I constrain, let's say, the fraction of dark matter using different observations? And so you can make some plot which looks like this, where on x-axis you may have k star, and on the y-axis you can put fraction of this exotic dark matter. And let's say the maximum fraction, of course, is 1. And then maybe in some logarithmic scale, this is 10%, this is 1%, and it goes all the way to 0.1% and so on. And you can ask where different observations live here. So the typical numbers that you will get from the CMB observations are, for example, such that CMB will rule out more or less this range of parameter space. This comes from the CMB. So CMB tells you that you cannot have more than 10% of this exotic component, okay? Roughly speaking. This, of course, depends on the mass, depends on the properties of the model and so on. But very roughly speaking, you have some numbers of this type. Sorry?
What does the EX mean and the X coordinate?
Sorry, this coordinate? The question was like, what does this coordinate k star mean? It is k star is just some characteristic scale which describes. So characteristic scale, I don't know if you know about neutrinos, but for example, or let's say any example of warm dark matter, this characteristic scale will have to do with the free streaming scale, which is associated to the mass of the particle, for example. In the case of the ultralight axion, there will be some characteristic scale which is related to the de Broglie wavelength of the ultralight axion. So for instance, if the mass of the ultralight axion is very, very, very small, then this k star will be very, 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 very small as well, and the other way around, okay? So now, if you remember what I said before, that things split between simple and complicated, let's say that this split happens somewhere here. In the regime where things get complicated, you also have very hard times making theoretical predictions which are precise enough. So for this reason, using data from small scales to constrain these models is not like always very easy. And indeed, I think that here the question is, how well can you, this is some astrophysics, some astrophysical observations of small scales can rule out a part of the parameter space of these models, but it is not entirely clear really how well, because you have to fight against many astrophysical uncertainties and systematic errors you can potentially put in. On the other hand, in the regime where things are simple and you can make precise theoretical predictions, it turns out that if you look at these typical examples and you do some forecasts, that you can actually significantly improve you can significantly improve these constraints from the CMB using galaxy clustering. And this is the regime and the region of parameter space where nothing else can really tell you what is the right answer, or there is no other way to make a potential discovery. So, for example, imagine that you have some, let's ask ourselves, where do the neutrinos fall in this plot, okay? So we know that neutrinos have a very large free streaming scale. So I didn't put any axis here, but it is, let's say, relatively close to the equality scale, so it will be somewhere else. So this will be K star for neutrinos. And then their impact on the, let's say, galaxy clustering is, roughly speaking, at the percent level. So they will be sitting somewhere here. So this point here will correspond to neutrinos. So this is the reason why we are trying to measure the neutrino mass using galaxy clustering and not looking at some astrophysical probes inside the galaxy on small scales, because those are very hard to control at the percent level. They can maybe give us a few percent or 10% effects to detect, but not 1% effect. And so if you have anything hiding in the dark sector, which has these properties that its scale, characteristic scale is like on cosmological distances, and it has a small fraction of a percent level or so, you can hope to find it. And you can find it uniquely using like these large-scale structural surveys and not, for example, in some other data. So this is the type of observations that we would like to make here. So in order to achieve this, in order to be able to fulfill this promise, we need to also have equally precise theoretical predictions, which are at the percent level or better. And I'm going to tell you a bit about that, how to do this. Questions? Yes, I see that the organizer is impatiently waiting to ask.
So where does weak lensing
the weak lensing is delocalized a bit because this plot is done in Fourier space, and the weak lensing picks up the information from like a lot of region in Fourier space. I think the weak lensing sits, roughly speaking, at the moment between, for example, for the DS data, the most of the constraining power comes from K around 1. So K around 1 is, roughly speaking, between this, in this transitional like region between like complicated and not so complicated regime, okay? So weak lensing gets most of the information from here, and you can see in the weak lensing that like, yeah, it's challenging to get things like perfectly correct in terms of theoretical predictions, and Rogerio mentioned some of these challenges. And we also see in the data analysis that the results move a lot, and they do depend on the particular choice of the analysis, on particular modeling, and so on and so forth. There is a convergence, and people, of course, the people learn more and more. They're more and more confident they're getting the right answer. But for example, like again, like measuring the neutrino masses from weak lens will be very difficult. This is a simple example where you can see that you cannot reach the same level of precision. The big advantage, of course, of weak lensing is that it can explore different parameter space where K star can be larger, but then you have to sacrifice a bit of the precision. Yes. Because the CMB, like this is one of these reasons that I was mentioning at the beginning. The CMB is very good in measuring lambda CDN cosmological parameters. If you introduce something that in the late universe, like imagine neutrinos, for the same reasons, if you go back and look at this plot here, you can see that the neutrino mass constraints are not very good for the CMB alone. They get much, much better when you add even very rough data, which is like just measuring the position of the BO peak in the late universe. The reason is that neutrinos like become non-relativistic at a time where like, and their main effect, which is gravitational effect, because they're non-relativistic, happens in the late universe. And so like CMB is not very sensitive to what is happening in the late universe. Anything that has to do with the peculiarities of dark matter, possible additional long-range interactions, modified gravity, dark energy, whatever you want, CMB is not very sensitive to this, because for CMB is sensitive to these things only through some integrated effects, like lensing or other things, but it doesn't directly measure what is happening in the late universe. And this is why it cannot tell you very precisely what is going on. One exception, of course, is the CMB lensing. So in the future, if you really, if you go to like ultimate CMB instrument and with a hope to get significantly better priors on the optical depth, you can get a very, very significant detection of neutrino mass. But I believe that it can be done like faster, or it will be done sooner using this galaxy clustering data. So let me, like before I to finish this motivation part, let me also mention one more thing. Why do we want precision, and how this precision versus robustness of going to smaller scales looks like from a different angle. Let me make another plot, which I always like to show because I think it's important to gain some intuition. And so in this plot, again, we are going to have some scale. We are again going to have some scale here, which I'm going to call the nonlinear scale, which basically is this scale which tells you that on one side you have something complicated, on the other side you have something simple that you may hope to control. And let us imagine that now we plot here two things. One is going to be some signal to noise inverse, which basically is how much constraining power you have on some cosmological parameter. It's a proxy for how well can we measure some cosmological parameters. And so you will see from like from Cora, and you may already maybe know, is that basically this thing goes like the volume of the survey times Kmax cubed to the -1, which is basically the number of pixels to the -1. So if you have a huge number of Fourier modes, or the number of pixels, then you have a very large signal to noise, and your error bars are very small. Okay. Number of pixels depends on the volume of the survey and how far do you go in Kmax. Okay. So in this plot, there will be some lines which correspond to different situations where basically they all scale in the same way with Kmax. So basically what I'm plotting here is the signal to noise inverse. And as you increase the volume, these lines are going down. So as the volume is increasing, the lines are going down. So what does this mean? It means that for the fixed Kmax, let's say you choose one Kmax, let's say K nonlinear. So for the fixed Kmax, you are going to achieve the same error bar. Sorry, for the fixed Kmax, like you're getting a better error bar from of course those surveys which have a bigger volume. Okay, so if you continue these lines, you will see that at a fixed Kmax, the bigger the volume you have, the things look better. Okay. Now the problem is that, and here we can put some numbers again, and let me put here, let's say 0.1% again. Sorry, this is maybe wrong. Let me plot signal to noise to the -1/2, which is really the error bar. So imagine that you want to reach the 1% error bar. Then basically, knowing the volume of the survey, you see how far do you have to go in Kmax in order to intersect this line of 1%. And of course, a very large volume survey will do it at a relatively low Kmax, while the small volume surveys have to go to very high Kmax in order to get to the 1%. Now, there is something that we always have to count on, and this is in a sense, a theoretical error. When we make theoretical predictions, they're never perfect. So on top of all other sources of error that we have in realistic data, we also have to worry about the fact that there is some theoretical error. And let's say that in simulations, roughly, it has this shape. It is more or less constant, and it is around 1%. So what this really means is that when these curves hit 1%, you cannot improve your measurement of cosmological parameters much more, because you're hitting like some ultimate theoretical noise that you cannot improve, and you don't really know how to beat it unless you make more precise simulations. So for example, if you want simulations which include all the baryonic physics and they predict galaxy bias and so on and so forth, like already being at the 1% is a very ambitious goal, okay? So in principle, you can see that no matter how big is your volume of a survey, you're going to hit this error bar more or less at the same time. And like, on the other hand, as I'm going to argue, in these analytical methods where we solve things perturbatively, let's choose another color. So the theoretical error in perturbation theory is usually much steeper. So it looks something like this. So now, so now you can see that the fact that it is much steeper, meaning that on very large scales, we can make very precise predictions. But on small scales, we have no idea how to predict anything. It has the following consequence, that if we have a small volume surveys, then we're going to hit this theoretical error for perturbation theory or any analytical method much sooner than we hit the error for simulation. And therefore, it pays off to have simulations because they help us to push things to higher Kmax and get better error bars of cosmological parameters. But as the volume of the survey is increasing, we may end up in a situation which is like opposite even, where you may hit let's say, the error from simulations in a sense around the same time or even a little bit earlier in a sense than what you can hit with the perturbation theory. And so for this reason, in the limit, when you go to very large volumes and for these future surveys, having like higher precision is more of a priority maybe than pushing to higher Kmax. Because the fact that you have such a huge volume will naturally cut you off on relatively large scales, and you will not be able to go much further towards a nonlinear regime, unless you significantly improve your theoretical modeling of all possible complications that live here, including baryonic feedback and details of the galaxy formation and so on. So is this clear? No, maybe not. So this is yet another motivation for why, looking ahead, there is really some value in having some high precision and not only trying to push towards higher K. Because you always have to remember that with a much bigger volumes, and as the statistical error bars are shrinking, having, let's say, 5% precise prediction for the nonlinear power spectrum at K of 10 is not going to buy you much. Unless you're looking for a giant effect, and let's say, then in that case, fine, you may discover something. But for this situation that I was describing here, where we're hunting for some small fractions of some exotic, let's say, dark matter component, just one example, having more precision is something that is more important in some cases. Okay, so this, I think, is all that I wanted to say about some motivation. And so now let me move on. Before I do that, are there any questions about this?
You may be able to the nonlinear regime, this simulation is matter only that you design, or?
Well, first of all, okay. So the question is like do we hope? So what does this really mean? Like, do we hope to get something more from simulations in this very nonlinear regime? And is this only for dark matter? And yeah, my answer is no. What I'm talking about here really is like, first of all, these curves are different and they depend a lot on the type of the tracer. They depend on the volume of the survey. They depend on like what kind of parameter you are after and so on and so forth. So in reality, things are much more complicated. But what I'm trying to illustrate here is that simulations can give you, let's say, a much better prediction on small scale than like any perturbative method, or any semi-analytical method. However, you may be in a situation where it's not useful for you, because if you have a humongous volume, your statistical error bars here will be so tiny that even, let's say, 1% uncertainty in the simulation, which is a big thing to ask, is going to be too much. So it is not enough to have 1%. You need 0.1%. And that then becomes exponentially more difficult to achieve, because there are many more effects that can appear at 0.1% and 1%, and so on. So I'm not saying that one should not go after this. Of course, we have to improve our knowledge on all scales as much as we can. But given the finite amount of time before the data arrive, like I would argue that it is interesting to focus on this regime, because and this regime is the fastest way and the simplest way to get pretty far without having to solve the whole problem at once. Okay, basically this is the main message here. Okay, so now I'm, of course, eventually we're going to consider the entire like the real problem of observing galaxies in redshift space and so on and so forth. But to build necessary tools and to gain some intuition for how these analytical methods work and what is the main logic behind it, I'm going to, for the first 2 days, do only dark matter, okay? Because it has all the complexity that we basically need to then understand things about tracers, galaxies, and redshift space, right? So now I decided to like basically present this in a historical way. I'm going to start with the wrong result and wrong equations, and we're going to discover together why is it wrong. And I hope that this way you get also to experience a little bit this moment in which you understand actually what went wrong, and then you will remember better, I guess, than if I just show you from the beginning what is the correct answer. So we are going to try to understand how to imagine that somebody comes and tells you, look, I have this simulation, N-body simulation, which has dark matter only. Can you make a theoretical prediction that can match what I simulate in the computer? Okay, so let's see how people try to do this historically, and then we will see why it doesn't work, and how do we understand today that it should be corrected a bit. However, I want to say that this will not be a waste of time, because a lot of tools that we are going to, or a lot of formulas we're going to derive here will be useful when we do what is a more correct thing tomorrow. Okay, so you have already seen that when we talk about the nonlinear dark matter, or dark matter in general, a very useful approximation in cosmology is always to treat it as a fluid. We always talk about various components as fluids in cosmology. And for example, in the CMB, this works very well, as you have seen in the lectures with Julien. And so you may think that perhaps starting with a fluid description and trying to use it for the dark matter in the late universe is also a good idea. And this is what people historically attempted to do. So let me write down the fluid equations at the starting point of this discussion, where basically, and then we move on from there. So we are going to assume, as people usually do, that the dark matter is an ideal fluid with zero pressure. And so if that is the case, we have basically continuity in other equations that we can write like that. Here, of course, phi is the gravitational potential, rho is the dark matter density, and this phi is the velocity of a fluid element. And of course, you know that in order to complete these equations, you also have to write down the Poisson equation, which tells you how basically this gravitational potential is sourced by the distribution of dark matter. Okay. So you may think that this is a good starting point, and we will see actually that that in fact it is not entirely clear later on. But if this is our starting point, we now want to solve these equations and see what kind of predictions they give. Now, here I wrote these equations, first of all, in the physical coordinates. So this r here is the real physical distance, and also I wrote it for the full quantities such as density and velocity of the fluid, of this fluid. But we know that these equations also have the background, which is more or less homogeneous and isotropic, and then there are small fluctuations on top of this background. We are not interested in the background evolution, that is just a simple thing given by the Friedmann equations. We are really interested in starting from here and deriving some equations of motion for fluctuations. Okay. So to do that, we are going to do several things, and I'm not going to go into all details, but I will just write down what is the final answer. So the first thing that we want to do is to split all these quantities into the background plus fluctuations. Okay. So, for example, the dark matter density can be written like rho bar, which is some background quantity, 1 plus delta. So this is the usual density contrast variable, delta, which let me just write explicitly. I'm sorry. As a function of space and time, is defined to be density as a function of space and time minus the background density, which depends only on time, divided by the background density. Okay. So this is the main variable that we are going to be after in this story, and this is the density contrast. Similarly, we can write the velocity like some v0, which is the background velocity, plus some small fluctuations delta v. And this v0 is given simply by the Hubble law to be proportional to the physical distance is r, and the proportionality, of course, is the Hubble parameter. And finally, we can similarly split the gravitational potential into some background gravitational potential plus fluctuations, which I'm going to denote with this small phi. Okay? So this is the first thing that we are going to do, and then essentially we have to, this decomposition has to be plugged into these equations of motion. The background equations of motion is going to be the usual things that you know from a homogeneous cosmology, and then fluctuations will have their own equations of motion. Now, the second thing that we want to do is to go from from physical to the comoving coordinates. So in the comoving coordinates, as Merdad mentioned this morning, x, which is a comoving coordinate, is given by the r over a, and the comoving velocity perturbation we're going to define to be this delta v divided by a as well. Now, when you do this change of variables, you have to be careful that the derivatives do not transform, that transform in a particular way, and the spatial derivatives go to 1 over a, and then spatial derivatives with respect to the comoving coordinates x, while the time derivative gets this extra factor. And this is very important because you will not get the right equations of motion if you don't transform the derivatives properly. So this is the second thing that you want to do. And finally, the third thing that you want to do is to use conformal time. as a time variable. Because this simplifies our life later on. It is not, of course, one can solve equations whichever way you want, but in the conventional way of doing things, we do these 3 steps, okay? And so then maybe I can leave it as an exercise for you to actually see that if you want to derive the correct equations of motion for the fluctuations, this is how they look like. You're going to have delta prime plus divergence of 1 plus delta v equals 0. So this is what the continuity equation becomes. And Euler equation is going to be vi prime plus conformal Hubble parameter h times vi plus vj dj vi equals minus di phi. And finally, the Poisson equation is just going to be 3/2 h squared omega matter, which in principle depends on time, times delta. Okay, so this is the set of equations that are satisfied by fluctuations. Okay. Right, so since we use now conformal time instead of the real time, prime here means derivative with respect to conformal time, which I'm also going to denote tau, unlike Julien, who called it eta. So, okay. So basically, we didn't do anything very complicated. We started with this assumption that the dark matter behaves as an ideal fluid. We started with the full equations of motion for the full density and velocity and gravitational potential. We split these variables into the part which is homogeneous, and these are the usual homogeneous equation, and the part which has fluctuations, and this is what we find. These are the set of equations that fluctuations presumably satisfy. Now, as we are going to see, these equations are not complete, and they are not consistent. Okay, at this point, we don't maybe know why, and if you don't know why, it will be interesting to understand, but that we'll do tomorrow. For the time being, we're just going to proceed and try to find essentially the solution for these equations of motion. Okay, so let me see. I think that so I think that I can skip basically this thing and tell you a little bit. So we have found these equations of motion, and now we want to solve them. So now there are 2 things that we need for we have equations of motion, but one thing that we need is like some initial conditions. And let me just briefly remind you that in the initial conditions are such that velocities are all 0. These are very special initial conditions, which also come from inflation, and maybe Merdad will say something about that. And the density fluctuations in the initial conditions are such that they that they're basically Gaussian. Let's assume that they're perfectly Gaussian for the purpose of these lectures. And they have some 2-point function, or the power spectrum, which is the so-called linear matter power spectrum. And I believe that you saw also these things earlier this week. So this linear power spectrum describes the statistics of these Gaussian random fluctuations in the initial conditions for the matter density field. And as you can see, this linear power spectrum has many features in it. So for example, on very large scales, the power spectrum is proportional, roughly speaking, to k to the power ns. And here, it inherits this shape from inflation. As you're going to see, inflation predicts the scale invariant power spectrum, which is approximately 1/k cubed. But for the so-called curvature fluctuations, which are related to the gravitational potential on large scales, since we are talking about density fluctuations here, there are two powers of k in each convergence from gravitational potential to density fluctuations because of the Poisson equation. So overall, there will be some k to the 4 multiplying the original power spectrum for curvature fluctuations. And this is why for the density fluctuations on large scales, the scale invariant power spectrum implies that the power spectrum goes roughly like k to the power 1, approximately 1. And the exact number is ns, which is, as you know, almost 1. Then we have various scales. Like for example, there is an equality scale around here where the shape of the power spectrum changes. And as Julian, I'm sure, explained to you, this has to do with the dynamics of fluctuations in the early universe, how the perturbation, the density fluctuations and gravitational potential grow or do not grow, or how do they behave outside the horizon, inside the horizon, radiation dominance and matter dominance. And this is a very important feature of the power spectrum. And then, like you can see here, the so-called BAO wiggles, which are the same baryon acoustic oscillation that you can see in the power spectrum of the CMB, the temperature power spectrum, for instance. And then at high K, this power spectrum roughly goes like K to the -3. Okay? So it has all the features which are inherited from the non-trivial evolution in the early universe. So inflation is going to produce a scale invariant power spectrum, and the non-trivial process in the early universe imprint various scales and various behaviors in the high K in this power spectrum. But for us, since you already studied this linear evolution last week, this is going to be the starting point. Okay? Let me only remind you that if you do the Fourier transform of this power spectrum, you're going to compute basically the 2-point correlation function in real space. And these BAO wiggles in the power spectrum become a single BAO peak in the 2-point correlation function. Okay? This is the famous BAO feature. And I showed you already how useful it is to measure some cosmological parameters. I will come back to that on Friday. Okay, so now let me also, when we talk about the linear power spectrum, I also want to introduce one quantity that is relevant in this story, and this is the variance of the density field. Okay. And so imagine that you start with some density field, delta, and then I would like to smooth it on a certain scale r. So smooth on some scale r, and the smoothing function can be anything you want, but for example, you can choose something like a Gaussian, which is basically proportional to e to the -1/2 x minus x prime squared over r squared. Now, smoothing the density field really means that you want to compute something along the following lines. You want to integrate over all possible points where you apply the smoothing function to your original density field delta. And if you smooth the density field, this means that you don't have any fluctuations of scales smaller than r. Okay, so now both not smoothed and smoothed density field are on average equal to 0 because they're just density fluctuations on top of the mean. So delta r is equal to 0. So if you want to compute the typical size of this delta smoothed on some scale r, what we have to do is to compute the variance. So the variance of delta r, which is given by this formula, is the expectation value of the square of the density field minus delta r of x squared. This thing is 0. And we can compute it going to Fourier space. It is very easy to show that actually the variance of the density field, delta r, and this is what Matthias mentioned in the previous lecture briefly when he was talking about these dimensionless quantities, is also sometimes denoted like delta square, which is the reduced power spectrum, is going to be given by the integral over d3k over 2 pi cube p of k, and then the square of this Fourier transform of the window function. So the window function is usually such that, for example, if you look at the Gaussian, it is such that it is approximately equal to 1 if the separation between points is smaller than r, and then it basically goes to 0 if the separation larger than 1. And so we can approximate the variance of the density field up to some scale k max can be approximated as the integral over d3k over 2 pi cube p of k up to some k max proportional or equal to 1 over r, which is approximately given by the formula k cubed over 2 pi squared p of k, where k is approximately 1 over r. And this is k max. Okay, so this number is very important because it tells you what is the typical size of density fluctuations in real space if you smooth them on different scales, or you're using different k max. Okay, and so it turns out that delta square is approximately equal to 1 for k max approximately equal 0.3 h over megaparsec at z equals 0. So at redshift 0, if you go back and look at the linear power spectrum, at redshift 0, the fluctuations in real space become of order 1 if you smooth them on basically scales of a few megaparsec, okay, which corresponds to k max of roughly 0.3 in this plot. And so this means that when we this quantity is important because it tells us at which point we can basically think of these fluctuations as being small and when do they become large. So on scales for k's smaller than k of 0.3, the fluctuations are small, and we may have some hope to treat them perturbatively, and this is what we're going to do. On scales larger than 0.3 megaparsecs, fluctuations become large, and at that point, we simply have to solve the full system of nonlinear equations, and there is not much that we can do about it. Is this clear? So have you seen all these things about the linear power spectrum already last week or not? Yes, okay, good. Okay, so the equations that we wrote before, and let me just maybe go back and copy them. So now we see that these equations are nonlinear. They're very complicated. They have these nonlinear terms. However, in the regime where this, for scales where this is less than 1, so for such case, we may hope to do things perturbatively. The fluctuations are small, so the significance of these nonlinear terms it cannot be as big as the linear terms, for example. And we're going to exploit this to try to find a perturbative solution. Of course, in the extreme limit, when so in the extreme limit, when delta square of k is much less than 1, we can completely drop the nonlinear parts. And then what we're going to do is to recover, I don't know. And then we're going to recover just the linear theory. Now, you have already seen the linear theory, I believe, in one of the lectures, or not really. Have you seen the linear equations for the? Yes? No. Okay. Okay, if no, then let me maybe do it, because otherwise there will be not much point continuing. So you have seen it? Okay. Then let me maybe just remind you very briefly, because I'm not sure that everybody is confident enough to say. You haven't seen them in the conformal time. Okay, but this is just a minor detail. I think that let me do the following. Let me just briefly remind you what is happening, and in case that you don't you don't recognize what I'm talking about, we can you can ask me the question. So in this limit, when fluctuations are very small, we can drop the nonlinear terms, and in that case, these equations become very simple. And what Laplacian, oh, sorry. Okay, so now the one thing that I want to mention is that since velocity is a vector, we can always decompose it basically as something which is v parallel plus v perpendicular. Let me call it like this. And this v parallel and v perpendicular is such that the divergence of v perpendicular is equal to 0, and the curl of v parallel is equal to 0. So this basically introduces naturally the composition of the velocity field into the part which is divergence and curl. And we can introduce two variables. One is theta, which I will define as the divergence of v, and the other one is going to be omega, which is going to be the curl of v. Okay. Now, looking back at these linear equations of motion, we can see two things. One is that this curl satisfies this equation of motion, which implies that it decays with time. And since it's not present in the initial conditions, at linear level, this vorticity is never generated. Okay, so we can forget about it. And this is why this decomposition is useful. And the second thing is that you have the equation of motion, which tells you that delta prime plus theta is equal to 0. And this means that this divergence part of the velocity is related to the density. And this makes sense, because if you consider to have an overdensity in some region of space, then the particles will be moving towards these overdensities and fluctuations grow. And this means that divergence will be negative. And this is exactly what of velocity field. This is exactly what this equation tells you at the linear level. Now, if you combine all these three equations together, for example, you can take the divergence of the second equation, use the Poisson equation, and then combine it with the first one, you will get what you have probably seen, a famous second order equation for delta itself. And solving this equation, you basically get the linear solution, okay? So you have probably seen at least some version of it. Now, this linear solution has both growing and the decaying mode. Usually we neglect the decaying mode if we talk about linear theory and focus only on the growing mode. And there are formulas to compute this growing mode, but you can simply just solve this differential equation. Let me just maybe mention that in one particularly simple example is when omega matter is equal to 1. And in this case, the so-called growth factor and the growing mode is simply given by the scale factor, while the decaying mode of this equation is given by the power of the scale factor, which is -3/2. Okay, and so probably you have seen this before, right? Now, let me see. Did I want to say something else here? Probably not, but is this all clear? So for the time being, we were just focusing on the linearized equation. Eventually, we want to find the full nonlinear solution. And to do that, first, let me note that at the nonlinear level, our equation for vorticity, 5 minutes, yes. You know, I'm aware of, sadly, that I'm running out of time. Like, so let me maybe just finish with a few comments and some setup for tomorrow. So at the nonlinear level, the vorticity satisfies the following equation. So you can see that our conclusion from the linear theory is true also at the nonlinear level. If the initial vorticity is 0, there are no terms which generate vorticity. In perturbation theory, this will remain true at all orders, okay? So we don't have to worry about the curl part of the velocity field. And we can focus then only on variables, 2 scalar variables. Actually, there's only one true variable which has a second order equation of motion, but we're going to keep track of 2 quantities. One is delta, and the other one is theta, which is just the divergence of V. Okay. And so, what we can do then? Let me just once again. Let me maybe finish with this, saying that finally, we focus on these equations of motion with basically using that the only relevant degree of freedom for velocity was divergence of V. As before, if this is the case, we can take take one derivative here, divergence of this equation of motion, use the Poisson equation, and basically end up with 2 first-order differential equations for delta and theta. And as another exercise that you should do, if you want to a little bit see how this calculation works, you can try to show that the following equations of motion are true once we go to Fourier space. Let me first say that I'm going to use the following Fourier convention. So, for example, the real space field is going to be integral d3k over 2 pi cube delta of k e to the I kx. And if you go to the equations of motion, these nonlinear equations of motion, and you write them in Fourier space, writing them in Fourier space is very useful because we get rid of these spatial derivatives and we have only simple ordinary differential equations in time. We are going to end up with something like that. Let me just write them down, and then this is where we're going to stop. Delta prime of k plus theta of k is going to be equal to q1, q2. Let me, by the way, say that this notation really means d3q over 2 pi cube. And here, we're going to have the momentum conserving delta function some momentum dependent kernel, which depends on the particular form of these nonlinear terms in the equations of motion and derivatives that act on them. and then solution, sorry, the two fields, theta and delta. And the similar equation for theta has the following form. This is equal to minus, again, some convolution of the two different fields. It will be the same 2 pi cube and Dirac delta of k minus q1 minus q2, and another kernel multiplying two velocity fields. So it is not very difficult to derive these equations. All that you have to do is to start from the real space formulas, do the Fourier transform, and then all these special derivatives are going to act on the exponents to give you particular momentum dependence in these quadratic nonlinearities. And these are exactly these alpha and beta kernels that I'm writing here. But let me just say that what they explicitly are. There are always some simple rational functions of momentum because we have very simple operation in Fourier in real space. There are either inverse Laplacians or simple spatial derivatives, and basically this is what we get. Okay, so now we have a system of differential equations which have some nonlinearities, and in principle we can just proceed and solve them. Okay, and we're going to see tomorrow what is the solution to these equations. We're going to see, sorry, I was too fast. Let me rename these variables. But yeah. So tomorrow we're going to see what are the solutions to these two equations, how we can organize them in the perturbative series, and what are the properties of these solutions, and how do we compute some nonlinear correlation functions, why this computation fails, and tomorrow I will explain how to fix it. Okay, but since I'm running out of time, I think that there is not much point in continuing at this point, and I will just stop here. Thank you.
Velocity plus the peculiar velocity, or is just the function?
This is the only peculiar velocity. If you remember at the beginning, we had this other v, which was like more like a Latin v, which had a part which was due to the Hubble expansion, which is the background, plus velocity fluctuation. So this peculiar velocity is like defined as fluctuation divided by a. You remember we were like introducing. I mentioned the window function because I wanted to tell you that one of the interpretations of the power spectrum is that the integral of the power spectrum up to some k max, which corresponds to 1 over r, is equal to the variance of the density field smoothed on the scale r in real space. Okay, I just wanted to give some now there is no need to introduce the window function. So at this point, we're just solving the original equations without introducing any window function. I mean, in fact, this will be one important point maybe later on. But for the time being, I'm just writing what would you get if you started with ideal fluid equations and follow like this procedure of splitting into the fluctuations in the background. What we needed this window function story for is to just get some idea about how to estimate at which scales the fluctuations become large. So if I smooth on like a very small scale, we'll get very large fluctuations. If I smooth on large scales, fluctuations are small. And we saw that for scales corresponding roughly to like order few megaparsecs, there is this transition between fluctuations being large or small. So we were focusing for the time being and actually for the rest of the lectures, on the regime where fluctuations are small. So k less than, let's say, 0.3 at threshold 0. So this integral here,
Yeah.
it does depend. It has two like theta fields here.
But not the delta.
Yes, the reason for that is in these nonlinear equations, as you remember, like here there are two velocities. So this is why there will be two thetas in the second equation. While here the nonlinear term has to do with delta and v.
Okay, let's find Marco again and recombine.
Okay.